To send raw, low-frequency audio or data, what engineers call a baseband signal, directly over a wireless link, you run into an immediate physical wall. Effective radio transmission dictates that the length of your antenna must be proportional to the wavelength of your signal. Because low-frequency baseband signals have wavelengths that stretch for miles, the required antenna would be impossibly massive. Even if you could build an antenna that large, you face a second blockade. If multiple baseband signals broadcast simultaneously over a shared channel without modification, their frequencies violently overlap, creating severe interference that renders all the data unreadable. The engineering solution to both the physical scale and the multiplexing constraints is carrier communication. By utilizing a process known as amplitude modulation, we can graft our low-frequency baseband message onto a high-frequency carrier wave, shifting the entire spectrum up to a manageable range. Modulation is a mandatory physical translation. Without it, information simply cannot survive the transit through the wireless spectrum. The clearest way to see this translation in action is through linear double-sideband suppressed carrier modulation, or DSB-SC. The operation itself is remarkably straightforward. We take our original baseband message signal, M of t, and multiply it by a high-frequency carrier sinusoid, denoted as cosine omega ct. This schematic shows how the operation is structured. In panel A, our modulating signal, M of t, enters from the right, and the carrier wave enters from the top. They converge precisely at the central multiplier to output the modulated signal. In physical hardware, performing this operation requires an analog multiplier. This is often achieved using a variable gain amplifier, where the gain parameter itself is actively controlled by the incoming message signal. Ultimately, this single act of multiplication in the time domain is the primary engine driving analog radio transmission. To measure the multiplier's impact, we look at the frequency domain. Panel B charts our baseband spectrum M of f between negative and positive B. Multiplication pushes the entire spectrum away from zero, relocating it to high frequencies, positive and negative Fc. Notice the geometry. Each translated pulse contains an upper and lower sideband. Look at the zero axis at Fc. The carrier generates no spike here, hence suppressed carrier. On the right, the carrier's oscillations are bounded by an envelope tracing M of t. The baseband information has been entirely erased from the low frequencies. It now lives strictly in the dual high-frequency sidebands, securely encoded for transmission. Pure mathematical multiplication is flawless on paper, but building perfect analog multipliers in physical hardware is expensive and difficult to scale to high radio frequencies. To bypass this limitation, engineers use switching modulators. Instead of multiplying by a perfectly smooth sinusoid, we multiply by a periodic square pulse train. Physically, this just means switching the message signal on and off at a rapid, precise rate. This chopping action scatters the spectrum across multiple harmonic frequencies. By passing that chaotic output through a bandpass filter tuned exactly to Fc, we extract the clean, desired sinusoid. It is a common reality in electronics. Physical circuit limitations force engineers to use crude, nonlinear switching to mimic linear mathematical ideals. Getting the signal across the airwaves is half the problem. At the receiver, we face the challenge of extracting the baseband envelope from high-frequency sidebands. This is a synchronous demodulator schematic. It must generate a local carrier wave perfectly matched to the transmitter. In panel E, the incoming modulated signal hits a multiplier and is multiplied again by this locally generated cosine carrier. In panel D, this second multiplication shifts the spectrum by Fc. Half the energy pushes into high-frequency artifacts at 2Fc, while the rest realigns at baseband 0. Finally, panel E's low-pass filter isolates spectrum A, rejecting the artifacts. This entire process demands exact precision. Without a perfectly phase-locked local carrier, the sidebands will fail to realign at 0, destroying the signal completely. Because homodyne receivers need precise synchronization, they're expensive to mass produce. Standard amplitude modulation became the historical workaround. Standard AM transmits a massive, continuous carrier spike alongside the sidebands. This allows receivers to rely on cheap, simple envelope detectors to read the signal. This trick is bound by the modulation index, mu. This waveform compares a safe index of 0.5 to an overmodulated 1.5. The baseline carrier amplitude A plus the message signal, m of t, must always remain greater than or equal to 0. If mu exceeds 1, the envelope dips below 0, creating a phase reversal. A basic envelope detector will trace this literally, folding the signal upward and permanently distorting the final audio output. Standard AM avoids receiver complexity, but at a severe cost. It purposely burns transmission power on an empty carrier, shifting the burden away from consumers. While DSP-SC solves the power waste by suppressing the carrier, it leaves a different inefficiency entirely untouched. If you recall the spectrum of a DSP-SC signal, it is perfectly symmetrical. The upper sideband and the lower sideband are identical mirror images. They carry the exact same baseband information. This is 100% spectral redundancy, burning exactly half of your available channel bandwidth to transmit duplicate data. Single sideband modulation, or SSB, doubles efficiency by transmitting only one sideband. This requires the Hilbert transform, shifting a signal's phase by pi/2. This intentional destructive interference perfectly cancels out the redundant sideband, leaving the desired one intact. The evolution of communication theory is an endless negotiation with physical limits. Engineers use increasingly complex mathematics, from basic time domain multiplication to calculated phase shifts, to continually squeeze more information into the finite geometry of the wireless spectrum.